about what she does at Northrop.
Thank you. Hi, everyone. Hi. I'm Sarah Beshir, for those of you who can't read. So I just want to give you a heads up. My talk is going to be way more dry and boring than Serena's, so please just mentally prepare yourself. Okay. So yeah, I'm Sarah Beshir. I work at Northrop Grumman. I'm also in school. It's very hard. It sucks. And I recently took a certification course at Caltech in model-based systems engineering and sort of fell in love with the subject. There are lots of potential applications at work, and I'd be happy to talk to anyone who's interested in career opportunities later. Also, please note the cool swag that I brought and not Serena. It says, it says careers at Northrop Grumman. All right. So the title of this talk is The What, Why, and How of Model-Based Systems Engineering. I misled you a little bit. The order I will be discussing this is actually the why, what, and how of model-based systems engineering. So please forgive me. All right, so yeah, the why, what, and how of model-based systems engineering. Can I just get a feeler, like how many people have heard of the term model-based systems engineering, model-based engineering, models? Okay. All right, okay. All right, so let me set up the problem. So I work in aerospace. I know people who work in the medical device industry, in, I don't know, manufacturing, product design. And an issue that is common amongst all of these industries is that systems of today are getting incredibly complex. They're so complex, it's impossible to find a single person who can grasp the entire system in their head, let alone capture it in a single document, which which you would give to your supplier. So we're dealing with problems and complexity. The reason we can no longer use our old system of requirements tracking or documentation is because we don't have the luxury of the linearity of like a small classic old program where you start with an RFP, a requirement specification, you move to design, development, launch, deployment, and maybe sustainment and decommission. Like, it doesn't happen like that anymore. Everything's super integrated. There are follow-on contracts that require integration into previously existing constellation. It's just very messy. So that also leads into the third issue, which is that it's difficult to perform impact assessment and prevent design escape. So a design escape is basically when something goes wrong. So yeah, that's exacerbated by increased complexity. So as you might have guessed from the title, I'm going to present a solution, which is model-based systems engineering. But I would like to first define the terms. So how many of you can say that they can comfortably define systems engineering? Yeah. Wow, you're the only one, because I can't either. Okay, all right, there you go. You cheated. Okay. It's a pretty nebulous concept. So systems engineering is classically defined as an interdisciplinary field that focuses on how to design and manage complex systems over their life cycle. This is the classic systems engineering V diagram. This is a simplified version, which sort of shows how you would progress from concept of operations through requirements, design, integration, verification and validation. And that big arrow that goes that way is supposed to indicate how everything is iterative throughout this process. So as systems get more complex, there is more iteration, more back and forth, less linearity. So we defined systems engineering, right? Let's define design and models. So this is not the type of model that I'm talking about. A model is any abstraction of a system, right, that can come that results in greater understanding, communication, explanation, or design, right? So a model is an abstraction. It doesn't necessarily mean that the abstraction is less complex than the system, which is something that we are concerned about, in systems modeling. Like sometimes you can have a really robust, pretty diagram, but you have to make sure that you're remembering the utility. So there's a balance there. So we talked about systems engineering, we talked about models, and so model-based systems engineering is sort of the unification or center between those. So model-based systems engineering is not only a visual representation of the system that you're trying to define, but it also utilizes a very robust database of information around each object in that model. So that can be values or equations that allow you to move through that systems engineering V, from design to integration and test, et cetera. Yeah, so the important part is building relationships between all of those elements. So let's actually take a step back. So how would we go about making these models? I had a mentor that showed me how in the olden days they would use PowerPoint to create interface design documents. So if you can imagine using a slide like this to define more than 150 ports, like it was disgusting. So today we have lots of really great tools. I happen to use Cameo. Cameo is a tool developed by a company called No Magic. Weird name, I don't know why. So these tools can help give you a more intuitive interface to help you draw diagrams, derive a model from existing code, visualize the models you want to make, run simulations, etc. So I'm not even going to show you all the capabilities of these tools. I'm just going to show you the basic type of models that we use, how we create them, and how they all flow together. So emphasis on the philosophical. These are, oh, I didn't realize the blue didn't show up. Can everyone read the top of those boxes in the back? So there's one box that has requirements at the top, behavior, structure, and parametrics. These are sort of rough buckets of the different diagrams that we use. I'm sure many of you have heard of like a functional flow block diagram or an interface connection diagram or something like that, or a requirements diagram. There are just a lot of them. So we have one level of abstraction, and this is one that I like to use. So there's gonna be a pop quiz later. So these are the 4 types that you should remember if you wanna win the thing. All right, so yeah, so for each of these categories, multiple ways to represent with different diagrams. And so let's make this a little bit more concrete with an example. I work in aerospace. What kind of systems do you work on? I think I hear that there are a lot of aerospace people here. But what else? Do we have anyone who works in medical field? Wow, that's so cool. Software. Power systems. Thank you. Is that? Oh, that's really cool and really applicable. Yeah. Yeah, I actually think model-based systems engineering has more applicability to sort of small system product design sometimes than large systems, because it's hard for us to move out of our legacy system, so you guys are really the early adopters. So the example I'm going to use, since I can't talk about work, is a hybrid electric vehicle. Anyone else own a hybrid here? Hey, Prius gang. Okay, so theoretically, you or your company or whatever has just won a contract for a hybrid car development. Okay, the customer gives you some guidance, but because this is a real-world example, we know that the customer's guidance is not to the exact level of detail that you need to move forward, thank you, with a systems specification. So you will be communicating and working with the customer to sort of narrow down what you want, or what they want, or both. Okay, let me take a step back. So the way we would approach this, right, we want requirements so we can move into development. But we don't have requirements. So let's first think about how we can get to that level of detail. So let's think through some use cases. What would be the use cases that are derived from the stakeholders involved in using a hybrid car? I was gonna like gray out the actors here and make you guys guess, but you got the answer. So key stakeholders are of course the driver itself, the driver, him or herself, may or may not be the owner, maintenance, insurance company, DMV. Feel free to shout out any others that you can think of. But in sort of putting together your understanding of the stakeholders with how they would actually use the system, then you can derive use cases that you would then break down further into getting your requirements documents and your system specification. So yeah, these are some use cases. The relationships between each bubble here can be, there are different types of relationships. Cameo gives you the facility to use different sorts of connectors to indicate an extend relationship versus an include relationship. And those, as I mentioned before, are connected to a relational database, which you can exploit later on. So we figured out our use cases. Now let's, so they gave us context initially, but now we want to sort of drill down into the needs of each stakeholder to help us develop requirements. So one example is like, say one stakeholder was the DMV, right? So the DMV perhaps has rules and regulations that dictate emission standards, and you would need to flow down those emission standards into the design of your car, right? That would be pretty important. So we could then create from that a requirement diagram, which presents sort of those classic text-based requirements, but includes their relationships to other requirements, design requirements, and even test cases. So later down in that systems engineering V, when you want to make sure that you've tested your system enough so that the customer is happy, you can just sort of run it through your model in Cameo or whatever tool that you use, and see that all of the requirements that are tied to test cases have been satisfied. Cameo, I really love Cameo, sorry. Cameo has really neat capabilities that would allow you to do things like auto-generate a document from a model, which is like, I don't know, like it's just really cool, guys. So it's like 2 mouse clicks, so you can go from this to, can I click this here? No. Will not let me. Okay, we're gonna escape. I just have to show you guys, it's so cool. Sorry, can I get some technical help? I messed it up. I don't know how I broke this. Can I just open up in like regular presentation view? Oh, here we go. Okay. Oh, I got it from here actually. Okay. Yeah, so it's this way. There we go.
Oh, and then if you just, here, I can help you.
It's loading.
Oh, okay.
Oh my God, you guys don't have Word. Woo! All right. So because this is a sample model in Cameo, this is not a very robust requirements document, but I just wanted to show how easily you can move from a model to literally a requirements report that you would give to your customer and call it a day. Sorry, how do I bring up the old presentation view? And now I have to just stand backwards. Sorry. Sorry. All right, thank you so much. All right, so we got to requirements diagrams. Now remember, requirements diagrams was one of the 4 categories. Who can remember the rest? I don't want to hear your question. That was one. Yes, structure. Who said behavior? I have one thing, guys. Okay, you're splitting the stylus. It's a stylus. All right. So the next category is behavior. So right. So as after we figure out the system specification, we can move into actually getting into the development of the system. So an activity diagram is a great example of how we would hash out that system behavior. Activity diagrams present a flow-based behavior, which indicate the order that actions occur based on the availability of their inputs, outputs, and control. And also they describe how the actions transform those inputs and outputs. So this diagram is a top-level behavior of an activity representing acceleration. As you can see, this is a breakdown of the accelerate function of that car. So we're allocating behavior to the parts of that power system that we saw on previous slides. If you guys are curious about what everything means in the model, that's an initialization node, an end node. These are ports, and in ports you can define how materials, energy can be accepted, in what format they can be accepted, and exit that action. This is a more complicated example of an activity of an activity diagram. Which just further explains how the physical and functional interact. So that's really the benefit of model-based systems engineering. It's not like a 2D. Theoretically, it's not 2D in that you really see how material energy flows throughout your system at different phases. The next level of system decomposition and depiction is the block definition diagram. How many of you have heard of a block definition diagram or have seen one before? All right, great. So we talked previously about what the power subsystem does, but the structural elements that it's really composed of, because that matters, right? You can talk until you're blue about how it actually works, like you get in the car, you drive it, whatever. But this is important when you're actually designing it. You can add to each object here. You can just like right-click, go into the specification, and define what units its values are, what are its subparts, how does it interact with other blocks. And as I mentioned before, ports are really important, which you will see here. Yeah. So these are more examples of ports which define interfaces. So we talked about block definition diagrams. An internal block definition diagram is just a sort of another more complicated example of the level of detail you can get into when you are defining a power subsystem or what have you. Okay, so someone else mentioned parametric diagrams. That was the last category or philosophical category of diagrams. So parametric diagrams tell tell you how all of the activities and the elements from those block definition diagrams and activity diagrams interact. They help you present constraints on property values, and they're used to support engineering analysis in many different ways. So you can see here that fuel flow relates to all of those other blocks by this flow rate equation, which is important, right? Like, you don't want to have a system that you develop that does not meet the constraints of nature. You don't want to design a system that doesn't follow like F equals MA or something. You know, that would be ridiculous. This is, again, a more complicated example of a parametric diagram with more equation constraints. The previous one had more value constraints. So we've shown, or I've shown, there's no one else here. I've shown how requirement type diagrams, behavior type diagrams, structure type diagrams, and parametric type diagrams all look, all of their subcomponents. And all I wanted to convey was that all data is related. And these tools are really helpful in your effort to not mirror the complexity, but like embrace the complexity of your systems in the diagrams and documentation that you create. So I'm sure all of you are buzzing with excitement now that you've seen all these diagrams. And you're curious, how might you acquire them yourself? How might you use them? So I have some good news and some bad news. The good news is that there are so many online resources, there are so many classes. If you work for an employer that reimburses you for education, hashtag Northrop Grumman, you can ask them to sponsor you while you take a class. The bad news is that these tools are really expensive. So Cameo and Rhapsody are kind of tricky if you want to get them individually. They're just a little bit pricey. Innoslate has a free online version, which is great, but it's kind of tricky when you want to use other people's work, which happens a lot. This book that I use and love, I brought. It's in the back if you guys would like to reference that. But other than that, I encourage you to explore online. There are so many applications for model-based systems engineering, from huge project scale to smaller project scale. It's really the future of systems development. And I hope you all can embrace the future of systems lifecycle development. Thank you. All right, for those of you who are still awake, who has questions? Oh, so many. Yes, you.
Hold on.
Oh.
I'm coming.
Speak loud. Shall I use the mic? Okay, got it. Okay, I hope I'm not the only aerospace engine background, but I have all going through all these things. So most of the things that you're talking about is a math. And when I remember when I was studying aerospace engineering and industry, 90% of the time is a math. So without math, strong math background, which is pain in the neck to do, it's not going to happen. But I also went to a facility before it was still Belize. But going back to the serious questions, most of the thing math, I remember mine was like a Reagan era background, aerospace engineering. So most of the thing we're using was a hand calculation. We're using the engineering paper. And as far as I remember, include me, all my friends, all my engineering friends, never made one calculation right. That's a reality.
Oh, because we're engineers.
Yeah, feedback. So most of the time talking about feedback control systems. So now we have these software programs. Are we getting better, or we're getting more stupid because we don't do the math at all? How close we're going to getting better or worse? That's a question. Thank you.
That was like a backhanded question. So I think we shouldn't be afraid of embracing new technology that allows us to adequately handle increasing complexity, right? So in Reagan era, I don't think you guys had coffee machines with like 8 different functions that could like make your whipped cream and like do your taxes. Yeah, yeah. So I think we're talking apples and oranges here, and I don't think from a private company perspective anyone wants to be under-equipped, right? So, yeah, it's a values question. Next, sorry, I saw you. I wasn't an engineer when I started.
Very damn loud. Apollo 11, 50 years later, that hunk of space rocket was hell of a
Beautiful.
complex, beautiful,
Yeah.
beautiful in its complexity, right?
Mm-hmm.
But obviously they didn't have these kind of methods. So does it like shock and awe you that that thing actually worked and people landed on the moon?
Absolutely.
Like, what do you know about how they designed stuff back then? What were the problems with that? And then of course, yeah, the modern solutions.
That's a great question. I think I have a lot of respect, of course, for the work that was done before me. You know, we're all standing on the shoulders of giants, and honestly, I don't think I could have done what they did. It's incredibly difficult. They had such little processing power. I really don't know how. Yeah, it was an engineering marvel, but every company wants to create the next engineering marvel. Hashtag James Webb Space Telescope. So, the purple hair lady.
Again. So they had about like a stack full of like 700-page documents back then and 300 PowerPoint slides with different things. But what's the most complicated model that you had to create, and what were the challenges and what was the result?
That's a good question. The most complicated, I haven't had to make a lot of these models for work, actually. It's mostly for fun. Actually, I don't want to be put on those programs yet because they don't have as much money as the old big programs, to be frank. But the most complicated model is probably this one, this hybrid electric vehicle. Yeah, but there are people making model at my site that are making models for 100+ satellite constellations using tools similar to this.
Sorry, I'll go right here.
Yeah.
So I discovered model-based systems engineering maybe a little over a year ago, and I developed a love-hate relationship with it, which I'm not going to go into because it's just too long. But one of the, I think, major barriers to adopting MBSE, or one of the value propositions of MBSE, is that you're getting rid of the ambiguities of natural language, right? And you're adopting a common language to speak among your team without any ambiguity. You're essentially working with a modeling language to communicate these very complex ideas, right? That being said, how do you actually get your team to adopt it? Because if you're the only person using this tool, then it's not very, very useful.
That's a great question. That's a great question that I think a lot of companies are struggling with right now. But like everything, money talks. And it's helpful when, the primary contractor or your customer is also aware of the benefits of model-based systems engineering and requests it or requires it in any work that you do. So there's that. There's also competition. So everyone wants to be ahead of the game. So even if a customer doesn't require it, if we see that a lot of other companies are doing it, it's giving anyone else an edge, we're more inclined to put up the capital cost to develop it internally.
Back here.
Cool. So it looks really cool to visualize the whole system. But now, if you want to interact with the system, are there functionality to do so?
Oh my God, yes.
Yeah.
Yeah.
Like if you put in a parameter, can you see the output somewhere, or?
Oh, sorry, say that again?
If you input a parameter, like a value for whatever variable, I don't know,
Yeah.
gasoline or something.
Oh, yeah.
Yeah.
Yeah, you would. So you'll be able to see the outputs in sort of other objects you create that relate to that previous object. So let's say, what was the example you gave?
I just say
Parameter.
gasoline, like fuel or.
So let's say you have a parameter for fuel type, right? And then let's say in your block definition diagram for the fuselage, is that a word? The thing where you put the fuel in. You connect it to that parameter and say that you establish a relationship in the database. You can if say later someone else tries to simulate the model with a different fuel input, you will get an error. Like literally, your simulation won't run.
Cool.
So it sort of prevents silly mistakes on the engineer's end. Sorry, this side. Oh, sorry, you're all the way over there.
I got it.
I see why you have that system.
Yeah.
So in a lot of my experience with debugging complicated systems, like a lot of the problems that you end up seeing are with interactions that you didn't a priori expect, like say in a system where you fire a defibrillator and you reset your microprocessor from some kind of electrical glitch. That's not necessarily you wouldn't have the problem if you could anticipate that there is that interaction. And if you're making a model based on what you expect are the interactions, I guess how do you
Predict for the unknown unknowns.
That's right.
There are unknown unknowns. You can't. I agree with you though. That is a primary concern. Because of the sort of nascent phase we are in with adopting model-based systems engineering, we're dealing with unknown unknowns even earlier in the design process. Like, how do you deal with integrating the tool with like doors or your other requirement software or something like that? I don't really have an answer for you. I will in 20 years though. Honestly.
So like one of the problems I run into super frequently, even on pretty small projects, is and like think particularly electronics projects, consumer electronics, something like that, is keeping track of what I thought was requirements, but in reality this very well addresses the sort of design complexity even on a small scale of like, I need a system over here that does a thing, and also the functionality of that system breaks when I do a behavior over here under certain circumstances. And if I'd thought about that ahead of time, it would have been pretty obvious, but like I didn't think about that ahead of time. Seems like this is what model-based systems engineering is designed to obviate. So the question is, like, to what extent, so first of all, is SysML actually like a language that I can write, or is it a like design paradigm the same way like getting things done is and requires software that implements it in order to exist? And to the extent that it's the latter, like how applicable is model-based systems engineering to a small project like that where like you simply aren't going to spend the financial outlay for tools like you use on a daily basis that do all of the simulation and stem to stern everything, but like I just need to keep track of my requirements and know I'm not stepping on my own foot.
So let me make sure I understand your question. Are you asking if SysML is a language you can write in abstractly,
That's the
agnostically
first
to tools?
Yeah, that's the first part. Does it exist independently of tools?
Okay. I've never tried to use SysML independent of the tools that translate to SysML. SysML is systems modeling language, so I assume there's a way, but I don't actually have an answer for you. Can you answer?
So SysML version 1, no. SysML version 2, maybe.
Okay. Thank you.
Okay. So SysML version 1 was a fork of basically
UML?
UML, an extension of a subset, but it was only designed for a graphical interface, which means they didn't create a formalized markup language for it, which you had to work with this ridiculous XML version of the thing that wasn't very standardized. So
Okay.
work with their adoption. SysML version 2 is a complete rewrite that's trying to make a more concise technical version that is essentially its own markup language, which is still kind of under.
So these days it is like an actual specified language.
It's
Cool. Awesome. Thank you.
Just a super quick question. How much do these programs cost?
You mean the tools?
Yeah. Like the...
I don't know if I'm allowed to say.
Yes, you are. Like, I can look it up. I want you to see it. Yeah. Come on, Sarah. We've known each other for a while.
I know that at a theoretical X company, it cost $50,000 for 4 floating licenses. But anyone on the campus of X company, you could use those floating licenses.
Okay, last question.
Okay, so on the follow-up on the question of how do you sell this idea to others, can you share your own story of when you realized, oh, wow, this is awesome. Why isn't anyone doing this? Like, what was your aha moment on this? Can you share that?
Yeah, it's kind of boring. I was in class, and a professor talked about it was one lecture at the end of the semester after we learned about the whole systems engineering process, how much drudgery it was. And at the end of the semester, basically, he was like, there are these tools you could use that would like do it all for you. It's really cool. You can work on more complex programs. And then we had to take the final. So my curiosity was piqued. I followed up with my professor, and he said that I should look into it. And then fortunately, my work gave me that opportunity.
All right.
Thank you.
Last question right here. No, you don't want?
Fine.
All right.
I'm kidding.
Are you sure?
Okay, sorry.
Okay, perfect.
Thank you so much, everyone. Can I make a quick mention? Can I make a quick shout out? So